I don't want any students to come into my office, you know, all 0 of the students that are here. Alrighty then, welcome to another 2DM3 lecture. We're going to cover set theory today, just a bit slower and a bit more application based. I know I zoomed through it last week, and because we covered propositional logic, there was nothing really new, and that was the point of the meta theorem 11.25, which just says, hey, sets, they're just Boolean algebras again, right? Sets, they're the same thing as lattices. So assignment 2, homework 10, right? All that order theory stuff applies immediately to sets, and that's why we didn't spend so much time on those. So let's. Someone had a question about sequences, so I will get to that at the end. So we'll just go a little bit slowly about sets, and then we'll get to sequences at the end. And if we run out of time, we'll me and whoever's interested, we can just talk about sequences afterwards, right? Okie dokes. Yes, so homework 14 was pushed back because some students, a lot of math students have other things to do. So we pushed that back a little bit. So speaking of math, actually, one of the things that maths people like to do is they like to treat everything as a set. Math people don't have types. Everything's a set for them. So because everything is a set for them, they can say, hey, let Q be the set of all sets S that do not contain themselves. So S is the set of all sets that do not contain themselves. Then the question is Q inside Q? Well, if Q is inside Q, then by definition, it must satisfy the property that Q has, which is not to contain itself. So if Q is inside Q, that's the same thing as saying Q is not inside Q. But a thing cannot both be and not be. You know, you can't be true and not true at the same time. And so we have a contradiction, right? And the reason for this contradiction is because the membership symbol for set people, for math people in particular, generally has a silly type, right? So the math view is generally, when you say in is of type set to set to set, all right? There are only sets, no numbers, nothing else. Okay, so math people don't really have types to constrain sets, and that's why you have this weird thing, right? So we're just going to talk a little bit more about sets. Eek, right? And Russell came up with this observation that, hey, if you only have sets, right? So numbers are sets, functions are sets, everything is a set, right? If you think this way, then you can end up with these weird situations where you can write down the set of all sets that don't contain themselves. And if this thing exists, if you can write this thing down, then you essentially have false as true, okay? And you never want to have false, so something is clearly wrong. And so mathematicians have reworked this to avoid having sets like this. They classify them into classes and conglomerates, and then they also have sets. So that they have this strange hierarchy. In computer science, we think, hey, how about you don't do that, right? So what Russell's main idea was, this membership symbol should have a type, right? So instead, we say membership is of type tau to set of tau to booleans. So this is the way we do it, right? Oh, sorry. So we make it into a different kind of predicate, right? Even booleans are sets, right? So in math speak, you can ask, is 3 inside 7? Is 3 a member of 7? Because for math people, membership is just set to set to set. Everything's a set. Booleans are sets. Everything's a set. There's nothing else except sets, right? So they're essentially untyped mathematics. Okay, so you can make this analogy that classic maths is essentially untyped programming. Right. This class is like typed programming. Okay, we have types to delimit how things work, right? A seat belt to stop you from crashing. Okay. And we've already met some types in assignment 1, and then again in assignment 2. We keep seeing types, and so we're just going to take a little breather and talk a bit more about types and wrap up sets today. Okay, ducks. If anyone has any questions, I am looking at the chat. So please let me know. Okay. So we'll talk a bit more about types today, and we'll see where we go from there. Hopefully, if we get some time, I would like to talk about relations today. But if not, no problem. We'll talk about them tomorrow. Relations and graphs. So we already talked about sets last week. So what I would like to do today is again to talk about sets, but this time to provide examples as we go along. So hopefully we'll have a back and forth. We'll chat about things and we'll see where things go from there. Okay, ducks. So sets again, a bit more gently this time. So, for example, you've already seen this general shape of sets. A set is a collection of things. It's like a list, but it's unordered. And this idea of having a variable that's being bound in the body and in the range, you've already seen this before. So let me show it to you. X with R spot P. So we've used P before. This is just the union over all X with R spot, and now you have P in curly braces. Okay. Quantifiers again. So all the quantifier rules, they apply again. So last week we said, hey, you can see sets from the point of view of orders and lattices. And now we're saying, hey, you've already seen sets. They're just a particular kind of quantifier expression. All right. So whenever you see a set, it's just a union of singleton sets. That's really all it is. Okay. So this is a theorem that maybe we'll have you prove later this week or next week, but it's a very helpful perspective to see them this way. Okay. There is a question. Hi, do you mind zooming in? I do not mind. I hope this is good. If you would like me to zoom in more, please let me know. Okay, I don't mind zooming in. Please let me know. Okay, ducks. You're welcome, Nasser. Nida. You're welcome, Nida. Alrighty then. So let's prove some theorems about sets. You know, it's easy to talk, but maybe it's a bit hard to actually prove some of these. So let me point out at some of the stuff you've seen before. This idea of abbreviation, whenever there's an abbreviation, you just use REFL. Okay, so let's do one together. Here's an abbreviation for you. Spot X. Who knows what this one will be? Let's have a guess. What do you think X spot X is? I'll go to the appropriate slide just to jump out here. Here. Does anybody know what it will be? So we've done this before, where we've said, hey, where we've written /sum of X spot X, for example, right? That means the range is automatically true, right? So this is just X with true spot X. And again, it will be checked just by REFL. Okay, ducks. So right there. So these are just abbreviations. I just want to on the midterm, for example, hint, hint, wink, wink, maybe, right? But you really should be familiar with these abbreviations. Okay, ducks. Please do not take control. Alrighty then. Are there any questions or concerns or queries so far? All right. So let's prove this little theorem. So what do we know about sets so far? So what we know about sets is the set membership property. Okay, and that's about it. That's all we know. So that's the only one we can use. So let's try doing that. E is inside X with P. Okay. Well, what does that mean? Well, let's just use reflexivity of equality to remove the abbreviation. That's E is inside X with P spot X. Okay. All right. So that checks out right there. Reflexivity of equals. Great, great, great. Now, the only thing we can do, the only thing we know about sets is that there's the set membership axiom. So we only have this one axiom right here. We don't have anything else. And we don't know how to simplify this expression any further. So let's try the axiom and see if that helps. So let's use the only axiom we have, set membership. Okay. The axiom says you can turn this into an existence X with the property P being true. And now we have X equals E. Okay. Hey, wait a minute. We have an equality inside a quantifier. Whenever you have equality inside a quantifier, that screams 1 point rule. So let's try doing that. So first we need to do trading, right? To bring those pieces apart. So also it exists X with X equals E spot P. So I've used trading twice there. Okay, to bring P inside and bring X equals E outside. But wait a minute, now that we have, you can pick any X you want as long as it's E. That's not really any choice. That's just called the 1 point rule, right? The illusion of choice. So that's going to be P with X becomes E. Okay, so that was a simple little proof. Nothing too difficult. Lots of fun stuff. Does anybody have any questions, concerns, or queries about that? Somebody wants to look at the trading. Yeah, let's do it. Why not? All right, it's important you get this. Thank you for asking. So when we traded, what we did was we said, hey, let's bring P in there. Okay, so we brought P in there, and then we did trading to take X equals E out. Okay, dokes? Good question, Tammy. Any other questions, concerns, or queries? So remember that heuristic from way back when, chapter 3, like at the very beginning of the class, we said, hey, when you meet new stuff you don't understand, which is this weird curly brackets and this weird epsilon thing, right? First, remove all the abbreviations. Then say, I don't know how to use this thing. Let me unfold with familiar stuff. So here we have some set theory stuff, and now we have no set theory. Look, all the set theory is gone. No set theory, just quantifiers and propositions, stuff you're already comfortable with. No more set theory. All that bad set theory gone. Okay, you're welcome, Tammy. So that's the main idea here. Just unfold all the set theory into quantifiers. Let's make a note of that. Unfold all the set theory into familiar, friendly quantifiers. Okay, so you can always just do that. Get rid of the set theory and turn it into quantifiers, and you're good to go. Okay, ducks. Just making sure. Nope. Alrighty then. So maybe let's. So here's two more. Let's try doing empty set and singleton set. See if I have them all set here for you. I do not have them. All right, that's fine, no problem. Boop. Theorem. Let's do this one right here, which is the empty set. So X with false equals the empty set. And we need a proof for this one. Okay, so let's begin the proof together. So here's X. I feel like I need to explain to you how we prove this theorem. So we're talking about the equality of two sets, right? So how do we show the equality of two sets? So if you recall, we had that the equality of two sets was via set extensionality, which says to show two sets, it suffices to show that they have the same kind of elements inside them. Okay, so the only way to proceed is to say, all right, we're using set extensionality. Okay, and then set extensionality says for any element x, right? So this right here, to prove two sets are equal, they should have the same elements. So we're going to show that for every set X, excuse me, we want to show that X is inside X with false precisely when X is inside the empty set. Okay. So let's that's a fun little thing. What's the empty set? Let's talk about that. The empty set is the set that has no elements in it. But let me. So just as 0 is the smallest number, right? So I have it all right here. We mentioned last time how empty set is like the bottom element, right? And so empty set has nothing inside it, right? So let's see how we can prove a property about that. Okay. Let me go back to where we were. Jumping around, not ideal. Okay. So by the previous theorem that we proved, that I just deleted, this is just false with X becomes X. Okay. And we said the empty set is the thing that has nothing inside it. And so we're good to go. But now we need the actual names that go in here. So here's symbol membership. This is the one that will go right here. And then the one right here, let's continue reading, and we'll get to it as we go along. Okay, next. Please do stop me if you have any questions or concerns, all right? The idea that sets are just predicates again is encapsulated by 11.7 and 11.5, which will eventually lead us to 11.25, right? Which says, hey, sets are just packaged up propositions. So nothing too new or too interesting. Okay, next. And as we mentioned last time, equality is pointwise. You consider each element. Two collections are the same if they have the same kind of elements inside them. For inclusion, everything that's here is going to be there. And so that's what it means to be contained in another set. Okay, ducks. And just as before, to prove set equalities, we can use the for any syntax. So nothing too complicated. So maybe let's stop for a moment and actually do some of that. So let me look through this notebook. Here's extensionality. So let's prove 11.6. 11.6 is a great theorem. Let's try proving that. So we're going to prove it using set extensionality. All right. So we're going to say for any x, all right, we're going to show that x is inside x with p spot e. Okay. And we're going to show that's equal to being the same thing as x is inside y with there exists an x with p slash spot y equals e. Okay. Now there's a reason I want to mention this theorem in particular. 11.6 is pretty neat. 11.6 is because we're using this bar spot notation, this quantification notation, right? Well, on the right-hand side, on the left side, we're saying this is a set of all x satisfying property p, so all the things with the p property, and we want to consider all the expressions e. So we want all the expressions e where x satisfies p. Okay. Now, because mathematicians don't have this kind of syntax available to them, they unfortunately have to phrase it somewhat awkwardly sometimes and say, we want all the y, which are of the shape E, so all the y's are going to have the shape E, and there is an x that satisfies the property P. So sometimes you'll see mathematical formulations like this, and it's a bit ugly and contrived. And so we're very lucky that we're using this bar spot notation, this linear quantification notation, also known as Eidhoven notation or Z notation. Okay, other places call it B notation. Okay, ducks. So this is what we want to show. Does anybody know where we should start? So I'll type and somebody maybe speak. What should I? What's the first rule here? How did the first step happen? Does anybody want to take a guess? Yep. Excuse me. Set membership. Excellent. Thank you. Multiple people are replying. Set membership is the way to go. The only thing we know here is there's some weird epsilon symbol and then some weird curly brackets, and we don't know what those are. We only know about quantifiers and the predicates. So the only thing to do is to get rid of it. This is that we talked about a moment ago. Okay, so let's make sure we're doing the right thing. Set membership, did that work? CalCheck found set membership. The theorem statement cannot be specialized in the proof. Oh no. Oh no, oh no, oh no. Why not? Set extensionality, yeah. Oh, because the goal is unknown. Okay. We want to show that for we want to show that for any x, these guys are equal. Let me rephrase this ever so slightly then. Let's use e instead of x, just to avoid, because we have multiple x's there. So just because then there's an x inside and an x outside. So x right here. So that's what that yellow arrow meant essentially. There's some x's that are being bound right here by the quantification, by the set comprehension, and then we talked about our own x up here. So to avoid that, we're just gonna call it e. We're renaming to avoid the error. And now notice there's no more yellow and the step went through. Okay, so when things are not making sense, try using different variable names. That's a simple takeaway. All right, so we simplified here. It's not clear what we should do. Should we try to use trading and simplify even further, or what? Well, what do we do? Not really sure what to do. So let's stop. We don't know what to do, and go to the bottom of the calculation and work up. Okay. So let's stop working here because we're not sure what to do, and let's work up. All right. So starting at the very bottom, x is inside y such that this property holds. This means there exists a y with, oh, sorry, we called this one e. There exists a y such a, so let's remove, somebody tell me what I'm doing right here. What did I do to the very first step? Does anybody know what I did there? And then I'll continue writing until people tell me how to fill these things in. Somebody says, yeah, exactly. It's an abbreviation. That's all we're doing here. And so that's reflexivity of equality, just to remove the syntactic sugar. Right? When there's no bullet, let's put that back in there. Right? Until you're comfortable, so here's the green just to show you. Until you're comfortable, I would recommend removing all abbreviations until you're very comfortable with all the syntax. So here, we're just saying the set of all y that satisfy this property. We want all y where y is a value satisfying this property. Okay, so how do we go from here down here? What's the main transition from here to here? Does anybody want to guess? Exactly. The only thing we know to get rid of that silly epsilon is called set membership. That's, you see an epsilon, use set membership. All right. See if that gets you somewhere. Okay. Now we're getting really, really close. Except this is called an x. This is called a y. They look very different. I don't know what to do. I'm scared. The world is falling apart. What do I do? Well, they don't look that different. There's a p right here, and there's the exists x over here, and there's an equals capital E. I have almost all of that right there. The only thing that's in my way is this silly y. How do I get rid of that silly y? So let's try to get rid of that silly y somehow. Just an x with p spot y equals e, and I want to get rid of that silly y. Okay, so here I introduce the silly y, all right, and that's just substitution. But what about here? What did I do there? Does anybody know what I did in that? Does anybody know what I did in that question mark? Okay, so here's one more question mark. How do we, reading from this line going up? How do we go from here up there? Does anybody know? No, exists introduction is not going to help. We're right here. We're here and we're going up. So how do we go from here upwards? All right. What rule suddenly says do a substitution? What quantifier rule says do a substitution? Exactly, Austin. 1 point rule. All right. So first thing we'll do is we'll do right. So trading will bring this y equals e to the range part, and then after trading we can apply the 1 point rule. Okay, and there you go. Everything is there. It's all green. Life is great. Okay. So hopefully many of you are comfortable applying multiple hints in each step in a calculation, right? It will save you some typing. Okay, folks. So if you really wanted, we could make this into golf by doing a lot of multiple steps in each hint. Lynn wants to see the step. Okay, dokes, Lynn, that's a good idea. Let's see the step. So we're down here and we're working up. The very first thing to do is to apply trading. So let's get rid of all that. When we apply trading, we're going to bring y equals e over here, and the other one goes over there. Now that we've applied trading, we can apply the 1 point rule. Okay, so when you're not comfortable doing multiple steps, take the breather, write a few more keystrokes, make sure you're comfortable understanding. Trying to do a lot in your head can be a recipe for disaster. Okay, ducks. So here it is, and there's the check. It's all green, and you know the world is great. Is there anything else regarding this calculation anyone wants to talk about? Okay, then we'll move on to cardinality, unless someone else has a reason we should stay here. Okay. Oops. Command. Oh, nope, wrong thing. Cardinality. No, it's not in this book. I don't have it in this notebook. That's unfortunate. So we'll talk a little bit about cardinality before we move on. So cardinality is defined to be the number of solutions or the number of elements inside a set. Okay, so we talked about it last time. It's just the sum of all x that are in S. For each one, we just add 1, just a counter. Add 1 each time. Okay. Of course, if S is infinite, like the natural numbers, then you're going to keep adding 1 for a long time. You know, so much time that you'll never be done. So this only makes sense when S is finite. Okay. So we say we say hashtag S is defined or well defined precisely when S is finite. It's like dividing by x. Division is well defined only when you're not dividing by 0. We say we say x divided by y is well defined if and only if y is not equal to 0. Likewise, we say hashtag S is well defined if and only if S is finite. Okay. So what does it mean for it to be finite? It means this expression is meaningful. Okay. Likewise, if you didn't have an idea of what 0 means, it means this division has a meaningful number. Okay, ducks. So we won't dwell too much on these well-defined in this constraints. So let's just look at a few examples right here. How many elements are? What is the value of this expression? Somebody want to take a guess? I will look at the message board and wait. I will wait all day. All right. That's exactly 2. Yeah, all right. It's 2. So there's one thing right here and another thing right there. That's 2 things. There are 2 things in there. What about this one? No worries. That's why we're doing it now. We're learning. So how many what is the value of this expression? There is one thing in that expression. Remember, sets don't care about duplication, right? Sets don't care how many times an element appears. So 1, 1, 1, 1, 1, 1, 1 is the same thing as just 1. So this has one element. Okay. What about this one? Yep. Good. It is 1. Excellent. What about this one? Excellent. It has 0 in there. What about this one? What about this one? How many things are in here? Exactly. There's one thing in this set. So here's the set, and the set has one thing inside it called the empty set. Okay. So remember when I talked about math people being a bit silly sometimes? So for math people, and this is, you know, it's fine in its own right. This is called logic ZFC, right? We use logic. We use logic E, right? This is for our book. So there are different logics. And in ZFC, they have 0 is the empty set. They have 1 is the set that has a single element in it. Okay. They have really suck n is the same thing as n union the set consisting of n. This is okay since n has a silly type. All right. Has the above ZFC type. Okay. So they have this weird thing where the number 0 is inside is the empty set. 1 is the set that consists of the empty set. And if you want the next number, you just union with all the other numbers. Yeah. Yeah. This is called ZFC type theory. It's a real thing. Real people use this. I don't like it. As far as I know, no programmer thinks this way. But math people do. So just be aware. ZFC. I don't call it sorcery, even. I call it a nightmare. I call it a nightmare. Like the type of union. Everything is a set, so it doesn't matter. There are no types. Like, it's the thing of nightmares for me. Other people like this, and that's okay. Everyone's allowed to have their opinions, and people can have wrong opinions too, right? So that's okay. So what is the size of this set? What is the value of this expression? Exactly, it's 1. All right, so there's one element in here, and that element is repeated multiple times. But we said multiplicity does not matter. So this element is, again, right here. So really, this is just like having this set up here. So there's one thing in there. Okay, next. What about this one? What's the value of this expression? This is your time to learn, guys. So there's only like 5 of you applying. The rest of you try, just, you know, put a guess. Don't worry. Just put a number down and we'll see what comes out. So how many, what is the answer here? Okay, so intersection means how many things are in common. So is 1 in both of these? Nope, so 1 is not in the result. Is 2 in both of these? Nope, 2 is not in the result. Is 3 in both of these? Yes, it is. There's a 3 right here and a 3 right here. So this thing, the result of this thing is just the set consisting of 3. And so the size of a singleton set is just 1. So the answer is 1. Good job. I see like 5 ones. Good job. What about this one? What's the size of this one right here? So there's 1, 2, 3 is repeated twice, but multiplicity doesn't matter. So there's 3, 4. There's 4 things in here. Good job. What about this one? Okay, so let's look at this. This is nice. You've seen this one already before, so we'll get to it in combinatorics, but now is a good time to mention it. Combinatorics. The size of S union T is going to be the size of S plus the size of T minus the size of S intersection T, right? So this is range split, right? So you've already seen this, right? The size right here, this is 3 elements, and right here that's 2 elements. So 3 plus 2 is 5, and then we said right here the commonality has 1 thing in it. So 5 minus 1 is 4. So range split, right? And you can prove this by using range split because it's just existence. You can prove it using just the fact that it's a quantification. Sorry, it's a sum. Okay, Dex? Okay. So let's move on to the next one, Cartesian product. So this means grab one thing from the bag and one thing from the other bag. Consider all possible combinations. So we're going to move later on into combinatorics. So now's a good time to show some examples of these. So this product, it's like having a double-nested summation. You sum over all possibilities here, and then inside you sum all possibilities over here, right? When you're forming the length, okay? And then a nested summation, well, we know what that is from quantifiers. So S times T, this is a nested sum. This is going to be for each possible S, for each S, we consider so this is 2, okay? 1 4 2 3 2 4 3 3 3 4. So it's just it's a nested union or nested quantification, if you like. So it has 1 3 1 4 2 3 2 4 and 3 3 3 4. So it has a total of, for each one of these elements, it has one of these guys. For each one here, for each one right here, it has one over there. And so that's a total of 3 times 2, that's 6. 6 elements. Okay, so just to flesh that example out further, 1, 2, 3 times 4, 5. This is going to be 1, it's going to be 1, 3. Okay, so we'll get into pairs into a moment. Sorry, 1, 4, and then 2, 4, and then 3, 4. Okay, and then it will be the second row, 2, sorry, will be, let me just copy paste. Command C, Command V, Command V. Okay, so for each one in the first case, we have one in the second case. So now it's going to be 5, 5, 5, and that's it. Okay, so it's just this bigger set. Okay. Okay, so for each one right here, 1, 2, 3, we pair them up with one of the elements over there. Okay, so for each one, we pair them with 4, and then we pair them with 5. And so we have a total of 2 times 3, which is 6. Okay, ducks? Yeah, all right, good job. Yeah, excellent. Okay, so we'll get to the notation in a moment, all right? So we didn't talk about it last time. We were really quickly, and we'll talk about it now. For example, using hashtag cardinality, we can say Jane called more people than Alex really easily. The set of people that Jane called, right, the size of the set of people that Jane called is greater than the size of the set of people that Alex called. So it's very useful to use hashtag sometimes. Okay. So here's a problem where we try to use a hashtag, and things might fail. So we want to say a function has at least 5 solutions, and we might formalize it this way. The number of solutions for fx equals 0 is at least 5. Okay. The problem is, for example, the sine function has infinitely many zeros. Okay. If there's infinitely many zeros, hashtag is not defined. Okay. So we can use quantifiers to make this clear. We can say there exists some set such that hashtag is defined and is at least 5. All right. So that means S has to be at least finite. Okay. And every element of S is going to be a solution to fx equals 0. Okay. So we get around the fact that there might be infinite sets by using a quantification to say, hey, even if there is an infinite set, we're only looking at a finite subset. Okay, so but in general, we won't worry too much about these distinctions. Alrighty. So we talked about the universe before, and so I just want to talk back again about it. So the universe is the domain of discourse. When we're talking about a particular collection of things, there's always some ambient there's some ambient context, right? What are the things we're talking about? What are these elements? When you say entity, what are you talking about? Are you talking about apples or people? Right? Are you talking about numbers or cars? All right. So when we say I have a set of things, what are the things? And that's what the universe of discourse lets us. That's what the universe of discourse clarifies. So whenever you have a type T, the set of T is a new type for all the sets, and then we say U is the universe of discourse, and everything is inside the universe, right? Everything is a thing. Okay, and we saw this earlier. The set of all things X such that true holds. This is the universe. Okay, so the set of all things is called the universe. That's what this theorem tells us right here. Everything is inside the universe. Okay. For example, when we're talking about booleans, the universe of the booleans is false and true. It's all the possible booleans. Okay. So for example, when we want to talk about things not being in a set, we say they're inside the universe, they have to be in the universe, but they're not in this part of the universe. Okay, so when I say I'm in the complement of a set, I mean I'm still in the universe, but not in this part of the universe. Okay, so that way we always remember where we are. Okay, so for example, if you consider the positive numbers and you say, hey, suppose S is a bunch of positive numbers. Okay. What if I want to consider the outside of S? The outside of S is going to be everything that is not a positive number, such as -5. -5 is not a positive number, but it's still a number, and so it's outside S. It's in the complement of S. Okay. Alrighty then. Let's go down to the next one. So a simple theorem says, hey, when you want to check that you're inside a set but not in the other one, if the first set happens to be the universe, you're just talking about the complement. Okay, so this is like saying 0 minus x. This is just negative x, right? Similar to that. Okay. So I skipped over power set a moment ago, so let's talk quickly about power set. So power set just says consider all possible subsets of what you have. Okay. So for example, how many subsets of 0, 1 are there? Well, there's the empty one, the ones that have singletons, and then the total one. Okay. So who knows what the size of this set is going to be? Let's have a guess. Does anybody know the size of this one? 8, exactly. And in general, right, because every set is either in a subset or not in the subset, so everything's either in or not, there's 2 options. We have that the size of the power set of S, okay, for any set S is always going to be 2 to the power of the size of S, okay, since everything is in or outside of a subset. Okay, so and again, we can prove all of these formally because it's all quantifiers. Okay, because hashtag is defined in terms of summation, we can prove these. Thank you, Dux. All right. So again, fancy P means power set. Okay. So let's consider a few examples. All right, since we're wrapping up with time. But the whole point of today is just to get you a bit more comfortable with set theory before we move on. And then the plan is to move on to relations. And then relations are great because they give us a nice way to get rid of quantifiers. So that's the reason we want to move on there. Okay. But to get there, we have to jump over sets a little bit. So the size of the universe. Who knows what number this one is? Just see. Yeah, thank you. All right. So the size of the universe is 2 because there are 2 booleans right here. Good job. What is the size of this set? Yeah, exactly. This one is 2 as well. This is the collection of all sets of the booleans that have true inside them. Okay, but we said the booleans. I pretend 0 is false and 1 is true. Then this is the power set of the booleans. You pretend 0 is false and 1 is true, and only 2 of them have true in there, right? And so that's why the size of this thing is going to be 2. Okay. So some of these you can just slowly work out, right? Actually, here is the power set of the booleans. The universe over all the booleans is the power set of the booleans. Okay, next. So if we want to consider set complement, the way we would type it is to say take sets to sets, right? It doesn't make sense to talk about the complement of a type because a type is not a set, right? So here's the key phrase to have. Sets are just another kind of data. They're like numbers, right? So when you say I have a number 5 and I have the type of the number 5, which is the natural numbers, okay, you can add 2 numbers. You can make you can negate a number, 5 and -5 or -5, but you don't negate the type of numbers. So this is set complement takes a set and it returns a new set. Okay, it doesn't work with the power set because the power set is in operation on sets. So they're different levels. Okay, next. So maybe I'll just make a note of that real quick. Negative works on numbers, and so we have 5 and -5, but it makes no sense on the type of numbers. Easy. Likewise, complement works on sets, right? And so has type set tau to set tau instead of mentioning p of tau, which is not a type. Okay, so this is a type of functions. Okay, so just want to reinforce that idea. So it's not. So I'm not trying to berate. Not trying to kill a horse with types, but we've seen them before, and just worried people might not be as comfortable. And now we're back at Meta Theorem 11.25, which just says, hey, sets are just propositions. Wherever see unions, turn them with or. Intersections, turn them with and. Complement is negation. Universe is true. Empty is false. Okay, and so whenever you want to prove a theorem, you can get all the familiar theorems we had before using this approach. Okay, and I want to talk about pair and Cartesian products, but I'm a bit short on time, unfortunately. So I guess we'll talk about those tomorrow. Yeah, I hope you all learned some cool stuff. I hope you're much more comfortable with sets, and we'll move on to relations tomorrow. And I'll stay after, and maybe we'll talk about some other stuff. Okie dokes. Alrighty then. Have a terrific Thursday. Bye.